Okay, so there are two ways we can do this. Guess and check is no doubt the easiest way. So if we just use our binomial CDF and vary the number of shots that we have. So just say I guess, I don't know, 20 trials, 0.4 success, at least once. So I need from 1, 2 and 20. So in reality, as long as that number there and that number there is the same, and then we just push equal to, and whatever that comes out on our calculator, 0.999963. So clearly it's over 80, but wouldn't be the first time over 80, so then we'd go back and guess and check a few others. Okay? The manual way in which we'd approach it is, all right, we're still going to need a CAS, but we want you to set it up. So what we need is the probability that x is greater than or equal to 1 is greater than 0.8. Yeah? So the chances of x being bigger than 1, and because we don't know how many games we're playing, it could be from 1 to anything. So instead, let's write that as 1 minus the probability that x is less than 0. So we might need to, which means if I rearrange things, that's the same as saying the probability that x is less than or equal to 0. It's got to be less than 0.2. So from my binomial rule, less than 0, which is the same as being equal to 0 in reality, because less than or equal to 0 is the same as equal to 0. So the probability of x being equal to 0 is equal to, well, however many trials we have as n, I need 0.4 to the 0 successes and 0.6 to the n minus 0 failures. That's got to be less than 0.2. NC0 is 1 by 0.6 to the n has got to be less than 0.2. On my CAS, that gives n has to be less than, in fact, greater than 3.15. Therefore, I'm going to need to have 4 trials to ensure a probability of success of more than 0.8. Okay? I could do the same thing with B, guess and check, but if I'm going to use a similar approach, at least twice, so I need the probability that x is greater than or equal to 2 to be greater than 0.7, which is 1 minus the probability that x is less than 2, greater than 0.7, which is the probability that x has got to be equal to 0, plus the probability that x is equal to 1 has got to be less than 0.3. Now I get that by taking the 1 across, actually taking the probability across and putting the 0.7 back, and realising that the probability that x is less than 2 is equal to 0 or 1. So using my binomial formula, I know I've got n trials, 0 successes, 0.4 successes, 0.6 to the n minus 0 failures, plus 1 success, which is 0.4 to the 1 times 0.6 to the n minus 1. That's got to be less than 0.3. So this first bracket gives me 0.6 to the n plus NC1 is just n, 0.4 to the 1 is 4, so 0.4 n times 0.6 to the n minus 1 has to be less than 0.3. Again, on my CAS, solve that. That gives me n has got to be greater than, greater than 6. Therefore, n has to be equal to 7. All right, part C. What's C telling us? What are the possible number of games one can play to ensure the probability of winning exactly 2 games? So we went the probability x equaling 2 is greater than 0.3. So this one's a bit more straightforward. So that's going to give me So the probability that x is equal to 2 is given by NC2 0.4 to the 2, 0.6 to the n minus 2. It's got to be greater than 3. So maybe we might need to simplify the NC2 a little bit first. So NC2 is actually going to leave me with n times n minus 1 over 2 times 0.4 squared times 0.6 to the n minus 2. I want to solve it equal to 0.3 first. That gives n equal to 3, that'll give me 3.13, or n equal to 6.2377. So in other words, n equal to 4 or n equal to 7, both give me answers. So they're both reasonable answers, but obviously n equal to 4 is the smallest number of games, so we'll probably go with that if nothing else is there to help us differentiate.